Hello everyone and welcome to the channel. In this video, we'll connect the clock and reset circuit to the CPU and execute its first instructions. We'll also build a bus display so we can see what's going on and have some blinking LEDs. I hope you enjoy! Okay, so in the past few videos, we've been building this clock circuit and this reset circuit. And so now that we have a clock and a reset signal, I think it's time to hook them up to the CPU and see if we can get it running. So let's do that. So the first thing I want to do is I want to wire up the clock into the second circuit. So we have to unplug this flip-flop here. This is what I was using in the past as a clock divider, but this is now built in our clock circuit. We have here on pin 6 the inverted clock that is going to the glue logic. And then on pin 5 the clock is going to the ready flip-flop. And it's also not connected currently to the CPU. So we need to add a wire here. We need to remove these wires here. And then we need to bring in the clock and the inverted clock from here to this side of the circuit. So let's do it. So the clock on the CPU is pin 37. So it's the fourth pin here from the right. There we go. We need to remove this wire now. I'm also going to remove this LED. This we don't need anymore. Neither do we need this. And this pull-up here, I'm just going to move somewhere else. There we go. So now the clock is going to the CPU and to the ready flip-flop. On this flip-flop, we need to tie all the inputs high. So that's pin 1, 2, 3, and 4. And there we go. Now the question is how I'm going to connect both boards. So I think I'm just going to use this 5-wire jumper, going from somewhere here to here. And so let's figure out the connections. So I'm going to need power, I'm going to need the clock, the inverted clock, and the reset signal. So I'm going to connect it maybe here. So the first one in red is going to be the power. Then we have ground. Then we have reset. And so reset is on pin 10 of this chip here. So I need to bring this here. Then I need the clock, which I already have here also. And then the inverted clock, which I don't have at the moment. And the inverted clock is on pin 6 here. This is what's currently driving the LED. So I'm going to remove temporarily the LED. And then this is the inverted clock. So I don't want to drive the clock LED from any logic lines, especially not the clock signals. So I'm going to use one of the spare inverters here to drive it. So I'm going to move it over there. So moving the label, so I'm taking the inverted clock and inverting it, and this gives us the normal clock. There we go, so this now can connect here. Up to here, so I need to move the power cables to the other side. And so we're going to have the same direction. So the first one is going to be the power, and things are a bit cramped here, but I think we can fit it here. Then we have ground. Then we have reset. And so reset, I currently have tied high through this jumper. It's pin 40 of the CPU, so that's the yellow wire here. I'm just going to remove this. So reset is here. Then we have the clock. And the inverted clock. Going to this pin here. There we go. Now we should be able to connect it. So we need to pull up the 3 interrupt signals of the CPU because we're not going to use them. And so that's pin 3, 4, and 6. There we go, and I believe this is everything. So right now in yellow we have ready in tied high, and in orange we have bus enable also tied high, and our 2 boards are connected. And so now if I power it up, I see that the power is coming here, and I should be able to clock it. Looks like I have a short somewhere. Okay, so I don't think it was a short, it's just a poor connection here on the power. But it looks like now it's executing. What we should do now is to set a value on the data bus to simulate the CPU reading something from memory, because at the moment it's only reading zeros because the data bus is pulled down and we have nothing connected to it. So I'm going to use my tester board here to connect to the data bus. And for now I'm just going to drive zeros on the bus. There we go. Let me stop the clock. What I'm going to do is I'm going to send an up into the CPU. And so this is EA. So in binary, it's 1110, 1110, and then 1010. So this is EA, and so this is the NUP instruction, and we should be able to start the clock now. Okay, so I've done some digging, and it looks like I have a voltage problem because the max 705 is constantly resetting. So this means that the voltage is below the threshold. So let's check this. Let's check the voltage at the inputs of the max 705. So right now we are at 4.83. But if I play a bit with my connection here, then you can see that this varies a lot. So let me increase the voltage in my power supply. I'm increasing to 4.3 volts at the inputs. And so now I'm getting 5 volts here, but yeah, the connection is really not great. And at the input of the CPU, I'm getting 4.85, which is fine. So I'm going to leave it this way, but I have to remember not to play with this connection. So now I'm able to run the whole circuit. So we see we are streaming NOPs into our read buffer here. Theoretically, the CPU should be executing that. So if I add my my display here to the address, so this should display A0 to A7. Let's add A8 to A15. So we can see it's doing something, but it's not what I'm expecting. What I'm expecting is it should increment the address as it's reading only knobs. Let's try to reset. Yeah, there is something fishy going on. Okay, so if I reset the CPU, which I'm not sure you can see here, the CPU goes into the reset sequence, and this is all correct. Then as part of this reset sequence, it is reading from addresses FFFC and FFFD. And then after that, it should jump to the vector represented by those addresses. And so because we are always sending EA into the data bus, we should jump to EA. And so that's correct. Now the CPU is reading from EA. It should get EA again, and it should increment this value here. So this is correct. Now it's again reading EA, which means it should again increment this value here. And then this happens. So this is the problem that we have. We seem to be jumping to 00 EA. What I want to do in order to help me debug this is I need to add a display for the bank address and for some of the CPU signals. So this is something I had planned to do at the end of this video. I wanted to first show it working and then do the display. But I think in order to debug this, I'm going to need the display. So let's build this. Okay, so first of all, we have tied all the interrupt inputs high. This is something that we're going to change in the future, but let's just reflect it in a schematic. And also, all these output pins currently are not connected, which means I should now be able to run an electrical rules check. So let's do that now. It says that here the wait signal is not connected on the schematic. That's not true. We do have a wait LED. So let me just add it here. And actually, since wait is active low, we want to tie the LED to VCC. What else? Power input is not driven. We need to add a power flag to our power input here. So KiCad knows where we are getting the power. Let's try again. Okay, and then this pin, the active high reset is not connected at the moment. Let's mark it as such. Does this work? Yes. Perfect. Okay, so let's add the debug circuit. So let me create a new sheet for starters over here. And I'm going to call that debug. Okay, so let's go into this sheet. This is going to be the debug module. All right, so basically what I want to do is to have a bunch of LEDs. So I'm going to get LED bars. So KiCad doesn't seem to have the 8-segment LEDs I'm using now, so I'm going to make a copy of this symbol. There we go. So we're going to have 4 of them. Each of them is going to go into a resistor network, going to ground. Actually, I'm going to first do one and then copy it. So something's wrong with my symbol. There we go. Now this is going to be D0. And actually what I want to do is I want to avoid driving LEDs from signal lines. The voltage levels of our logic signals are defined for a specific current. And if you overload the chips, then the voltage at the output of a logic gate can change. So generally I tend to avoid driving LEDs from logic gates. For example, if you look at the datasheet of the 74HCT245 in the electrical characteristics, you can see that it's specified for an output current of plus or minus 6 milliamps. So if you go above or below that, there's no saying what the output levels are of the chip. So you want to stay below this. Additionally, you can see in the absolute maximum ratings that the continuous output current for one output is 35 milliamps. So you could theoretically drive 35 milliamp through a single pin. But the continuous current through VCC or ground, that is the sum of all the current that you're currently sourcing or sinking, can be a maximum of 70 milliamps. Since this is an 8-bit buffer, you can see that the absolute maximum rating, if all the inputs are turned on, is 70 divided by 8, which is 8.75 milliamps. So it would be pretty easy to overload such a chip. This is why I'm going to add it in front of all the LEDs. So this way I'm guaranteed that anything before the buffer is isolated from the current draw of the LEDs. And then I don't actually care about the voltage levels at the output of the buffer. They can drop as necessary to drive the LEDs, because I'm not going to use this side of the buffer as a logic signal going into another gate. So it needs power and ground. And then chip enable is going to be always enabled. So we're going to tie it low. And then the direction, since we want the data to flow from A to B, we need to tie the direction high. There we go. So now we are able to display the contents of the data bus in a safe way. I'm going to copy this 3 more times for the address bus. So this here is going to be the address bus display. There we go. And I'm going to add another one for the control signals of the CPU. So these are going to be RW, read write, VDA, VPA, and I'll talk about VDA and VPA in a future video, as well as the RQ signals and NMI as well. Okay, so now we have to think about the polarity of our signals. So we may want to invert some of them so that the display makes more sense. So I want to invert the read-write signal because I want the LED to light up when we are writing. VDI and VPA can stay with their regular polarity. I want to invert RQ because I want the LED to light up when we have an RQ. I want to invert ready because I want the LED to light up when we are bringing ready down, which shouldn't be the normal case. Same thing goes for bus enable. If we bring bus enable low, I want the LED to light up to tell us about it. I also want to invert NMI and wait because those are active low signals. So as you can see, there's a number of signals that we need to invert. I think it's simpler if we just flip the LED bar and connect it instead to VCC on the other side. So this way all the signals are inverted, and so now we need to invert VDA and VPA to restore the correct behavior. So I'm going to add a 74HC04 hex inverter. We're going to take VDA and VPA and we're going to invert them. Okay. So this should be the correct display. So we need to add all the spare gates of the inverter and connect the inputs to VCC. We need to connect power and ground to the inverter. And we need a number of decoupling capacitor. So we have 1, 2, 3, 4, 5, 6 chips. And then we need to set up the sheet IOs. So we need to input all the control signals. We also need to input the address bus and the data bus. I'm not actually sure of the correct notation here. I'm going to look that up afterwards. Okay, so now let's set up the buses. So this is the address bus and this is the data bus. There we go. Okay, so let me move this here and resize it because we're gonna have a lot of pins. Okay, so let's import the pins. Now we can probably actually remove this LED. And I'm calling this label WAI, like the instruction. So error W, we have a label, VDA and VPA, we need one. So I'm going to remove the no connects here and add the label. Oh, actually, I swapped them. Same thing for the RQs. Let's remove this. There we go. So this should be everything. Okay, so let's implement it on the breadboard. Okay, so I'm going to focus on the CPU board. I'm going to add 2 breadboards. There we go. So I need to connect the power. There we go. I have here 5 74 HCT 245 buffers, which I'm going to add now. And a 74 HCT 04 inverter. All these chips need power and ground. And decoupling capacitors. There we go. Now I'm going to add the LEDs with the resistor networks. Now the common pins of the resistor networks need to go to ground, except for the last one, which is going to be the control signals of the CPU, and so I'm going to tie it high. On the buffers, we need to tie the chip enable low, that's pin 19. And we need to tie the direction pin high, that's pin 1. There we go. Now we need to connect the buffer outputs to the LED. And for that, I have a bunch of pre-cut wires that I'm going to use instead of cutting like 32 small wires. There we go. Let me test the polarity of the LEDs. Okay, so yep. This one is reversed. Okay, so now I need to connect the data bus and the address bus to the CPU. So in order to free up some space here, I'm going to move all the pull-ups and the pull-downs to here. So I am pulling up the address bus and I'm pulling down the data bus. So through the magic of video editing, I've now connected all the 32 wires of the address bus and the data bus. And I also figured out why I was having problems with the CPU. The reason is this output here is least significant bit first, and I was inputting an up with its most significant bit first. So I've reversed it here so that on the display it's most significant bit first for all the binary displays. I'm also going to connect the control signals to the display. So let's do that now. I've put them in a specific order for a reason that will be revealed later. The first signal on the left here is going to be the read-write signal. So that's this one here. The second one are going to be the inverted VDA and inverted VPA. So we're going to take them from here. So VDA on the CPU is pin 39. So that's this one right here. VPA is port number 7, which is down here. Then we have IRQ, ready and bus enable. IRQ is pin number 4. And I'm going to move the pull-up next to the buffer. So pin number 4. And I know that my wiring is really not great, but that's okay. So just need to put back the pull-up for the board pin and add the pull-up for ARQ here. Then we have ready and bus enable. Ready is pin number 2. And bus enable is over here. Then we have NMA and wait. So NMA is pin 6, this one here. Also going to move the pull up to there. There you go. And the last one is wait, which is where we have our LED. So now I need to tie all the unused inputs of this chip high. And this should be everything. Let me bring in the clock and the power. Okay, and we see the CPU is executing something. Now how well you can see those bars. Right now it's just completely random. So I'm gonna try the no ops again. And I'm going to plug my board here. This way it's the right way around. There we go. Okay, I'll figure out a better solution for next time. So now if I reset the CPU, we can see it starts the reset sequence, loads the reset vector, and then keeps incrementing the program counter. So it looks like it's working. And the two LEDs that are flashing here is VDA and VPA. And so that's when we are loading the opcode for the knob. All right, so there you have it. First time we're running the CPU. Really excited about that. All right, so one thing I want to try, now that we're able to send instruction to the CPU, is I want to try to trigger the wait output. We've been talking about that in a couple of videos, and we haven't been able to test really this circuit. This to me is an even better test of the CPU because we can have it do something instead of just executing naps. So the opcode for the wait instruction is CB. So I'm going to put the CPU in pulse mode. Now I can change the instruction. So CB is going to be 1100 and then 1011. So this is the wait instruction. Let's see if it actually makes the CPU wait. I'm going to clock it. So now it's loading the instruction. And it's waiting. The LED came on. And also the last one here. And ready has been brought low. So this all seems to be working. So now if I try to clock back my naps, so I go back to 1100, 1010. And so now if I try to clock more naps into the CPU, nothing happens because the CPU is in a wait state. That's really good. And so in order to reset it, I need to generate an RAQ, and that we'll talk about later. So now I'm just going to hit the reset button. I have the reset sequence here, then it loads the reset vector, and then it continues executing. Awesome. Really excited about that. So there's a few things I want to fix. The first one is this power thing. When I power the board from all the way up here, depending on the connection here, sometimes the Max 705 detects a brownout. So I think not enough voltage gets through to here. So I have to fix that because this is really flaky. And then we don't really need this whole board anymore. I'm going to take a minute and move it to a smaller one with just the dip switch. So let's do that now. There we go. This was the source of my power problems. So this was going to my power supply, and then I had those alligator plugs here gripping some DuPont cable, and the connection on the breadboard was really not great. So I fixed it. So I've made my own cable here, some banana plugs going into a long cable. This is a plug that I can unplug when I want to remove the power. And then this is going to pin headers. I don't know how well you can see that, but it's basically a wire connected to 3 pin headers, which should provide a pretty good connection on the breadboard. So let me install that. There we go. I'm also going to move the big power capacitor and the power LED here, and let's turn on the power. And you can see it's working much better. At the Max 705, we are getting 4.9 volts. So that's pretty good. Since it's going through this cable, going all the way around, going to the Max 705, and then here it's all those cables. I only have a loss of about 0.1 volts. So that's good. And I also said I would be sprinkling some 10 microfarads capacitor on the power rails, but I really haven't done that. So I'm going to do that as well now. And so these are going to help with the power. They keep charge around the breadboard so that when a chip is switching here, it doesn't have to fetch power all the way through the power cables to the power supply. It's a bit of a similar role to the decoupling capacitors I'm adding everywhere, but just in a more bulk capacity. There we go, so I added some of them. All right. Okay, I'm just going to add just a little dab of hot glue here so that the pins stay together. So now I can remove them and they don't make contact. Okay, so in this video we've added the reset circuit and the clock to the CPU board. We've also added this bus display here that shows us what's going on with the data bus, the address bus, and the control signals of the CPU. And by using our little tester board here, we're able to send knobs into the CPU and have it execute them. In the next video, we'll discuss the memory map of the CPU and we'll start hooking up some ROM. So I hope you enjoyed this one. Let me know in the comments if you've got any questions or feedback. And I hope to see you in the next one. Goodbye.